Welcome to the Week 4 lecture of Microprocessors and Robotics. This week I'll be reviewing some of the results of Homework 2. We'll also be reviewing for Exam 1, which will be next week. We'll be taking a look at, as far as programming goes, we're going to look at branching in your programming, programming in loops, jumps, comparisons, and then I'll review Lab 2 a little bit, and some Lab 2 examples will be in a separate video. I noticed some trends when I was going through and double checking the results of Homework 2. A lot of common incorrect answers to a couple questions, so I just want to review those and help you understand the concepts of some of these and cement that understanding. So a lot of students got question 2 wrong. That question asked you to convert the following decimals from signed binary to a decimal number. And what happened on this, if you missed this question, almost all of you who missed this converted from 2's complement to decimal. So you converted as if these numbers were 2's complement, when in fact they were signed binary. So just a quick refresher, I have a little kind of caption down here from our week 2 presentation. Signed binary numbers, the most significant bit is a 1 if the number is negative, and the most significant bit is a 0 if the number is positive. And so 2's complement is a little bit different, right? We use that to convert negative numbers most of the time, and that involves inverting and adding 1. So signed binary, we don't need to do any of that. We just need to recognize that the most significant bit is just representing the sign of the number, and the rest of the bits are representing the number. So in this little example I have down here in this inset, we see positive 5 is just the binary number 5. And we use 4 bits to represent that, so that the most significant bit is a 0. That represents a positive number. Now if I needed to make this a negative 5, you'll see over here where I've highlighted, that most significant bit changes to a 1. And then after that is just the typical binary representation of the number 5. So now I have pulled these 4 numbers in bullet points back on the left from your homework. And so I just want to review these real quickly. The first number, we're looking at the most significant bit, and we see it as a 1, so we know that this should be a negative number. And then if you'll recall the place values, we know that this first place value here after the most significant bit, this will be a 2, this will be a 4, and the one after it will be worth 2 in decimal value, and of course 0 is 0. So 4 plus 2 is going to be 6. This would be just these last 3 digits would be the binary representation for the decimal number 6, but because the most significant bit is a 1, that makes this number negative 6. And so looking at this next example down here, the one below it, we see again our most significant bit is a 1, so we know that this will be a negative number. And this one's pretty easy. We should know that this bit right here that I've just highlighted, this is worth 2. That has that place value of 2. And the second one over here, 2 to the power of 0, so this has a place value of 1. So 1 plus 2 is going to be 3, and again we know it's a negative because of that most significant bit, so this will be a negative 3. So notice, again, just to reiterate, when you're converting from signed binary, it's not like 2's complement. You're not inverting, you're not adding. It's just like a typical binary to decimal conversion, except this most significant bit is representing the sign. So going down to this next example here, we see our most significant bit is a 0, and so we know this is going to be a positive number. And so I'm not going to go through all these place values, but the value of this number is 78, and we know it is positive. So that's going to be a positive 78. And then let's go down to this last one. We see the most significant bit is a 1, so we know that this will be a negative number. And again, if we go through all of these place values, guess I can do that. So this first one, let's start on the right side. It'll make it easier to count up. So this first place value is going to be a 1. And then of course this next one would be worth 2, but there's nothing there, so it's a 0. And then we have a 4. And then so we have 8 in this next place value, but there's nothing there, so it's going to be a 0. This next one is going to be 16, 2 to the power of 5. I'm sorry, 2 to the power of 4, so that's 16. And then this next one is going to be 32. So we have 32 plus 16 plus 4 plus 1, and that equals 53. And so again, because this most significant bit is a 1, that makes this a negative. This is negative 53. So hopefully that clarifies how we convert signed binary numbers to decimal numbers. Another question that was commonly misanswered from homework 2 was question number 5. What is the largest decimal number we can represent with a 5-bit 2's complement number? Common answers to this question were 31 and 32. But in fact the answer was 15. So I've inset again this slide covering this concept from week 2, and we'll go ahead and review the 2's complement number limits. So as a refresher, when we use 2's complement, we can only represent numbers according to these two formulas that I have written here. And so the first formula represents the smallest number that we can represent, and the second formula is for the largest number that we can represent. So if we take a look at these examples again in this slide, if we're working with 4 bits, n is our variable. It represents our number of bits that we have to work with. So we'll plug this into the first formula to figure out the smallest number we can represent. So that's going to be negative 2 to the power of 4, because we're working with 4 bits, minus 1. And so negative 2 to the power of 4 is going to be 8. I'm sorry, negative 2, this is 4 minus 1, so it'll be actually negative 2 to the power of 3, which is negative 8. And so that's the smallest number we can represent. And so the largest number that we can represent is if we plug numbers into the second formula. So 2 to the power of 4 minus 1, again, which is 8, and then minus 1 is going to be 7. So the largest number we can represent with 4 bits is 7. And so coming back to our example over here, we see that we're working with 5 bits, and we will be using this second equation to figure out our largest number. So if we plug the number 5 as our variable in for n into the formula, here's what we end up with: 2 to the power of 5 minus 1, and then minus 1 from that. So we'll just go through and simplify step by step. 5 minus 1 is 4, so another way to write this is 2 to the power of 4 minus 1. And then to simplify even further, 2 to the power of 4 is 16. And then we still need to subtract that 1, so we'll copy that over. And then 16 minus 1, of course, is just 15. So 15 is the correct answer for question number 5. A lot of you answered 31 and 32, and I think what you were thinking is just the largest decimal number that we could represent with a 5-bit binary number. And so if we had 5 bits in binary, we maxed out all the 1s, we could build the decimal number 32. But I think what you forgot to account for was that it is a 2's complement, and so that's a little bit different because we need a most significant bit to represent the sign. And so when you're figuring out the maximum or the minimum 2's complement number, make sure that you're using these formulas. Something else of note was that I believe a lot of you, question 6 was counted as wrong, even though you got it right. And so a lot of you answered correctly. The answer to question 6 was negative 16. So if we follow this example again, the smallest number that you could have, and I did give you a hint that it would be a negative, so we would follow this equation. Negative 2 to the power of n minus 1, that of course would be negative 2 to the power of 5 minus 1. Negative 2 to the power of 4 is negative 16. And so if you answered negative 16 to question 6, that was correct. The answer, unfortunately, I apologize, was a typo. So I went back and changed that, and all of your homework 2s have been regraded to reflect the correct answer to number 6. The next question that we'll be reviewing from homework 2 is question number 9. This involved converting decimal numbers to their 6-bit 2's complement if necessary, and then adding them. And so I was surprised that many students had incorrect answers for this question. Most of you were able to successfully convert to 2's complement, and most of you were also able to successfully add two binary numbers, but for some reason when it came to putting those concepts together, there was some faltering. So we'll go ahead and review those now and hopefully be able to clarify some things. So 16 plus 9 was your first question. And just a reminder that when we're working with positive numbers, we don't need to convert them to the 2's complement, right? 2's complement was invented so that we could add negative numbers, so that they would be added properly. So you can convert positive numbers if you wish, but you don't have to. And so I won't be making it harder on myself, right? I'm not going to add that step, so I'll just be using the typical binary number here. And so I've also added this little chart at the bottom just to remind us of the place values. So if you need to, that can help you make these numbers make sense as we go through. I will explain this first one here. So we have 16 written in binary form. This one's pretty easy since you can see down in our chart we actually have a place value of 16. So we just put a 1 in that place value and zeros everywhere else. The next one is the number 9. So we have a 1 in the place value of 8 and a 1 in the place value of 1. So this is our binary number 9. And so going through these two numbers now, just to add them, we'll go down here real quick. 0 plus 1 is 1. 0 plus 0 is 0. 0 plus 0 is 0. 0 plus 1 is 1. 1 and 0 is 1. And of course, 0 and 0 is 0. And so you can see if you converted this back to decimal, it would in fact equal 25, the correct answer. We also notice that there's no carry out. There's no carry out here, and there's no overflow because this most significant bit right here is a 0 that represents a positive number, and so we're perfectly fine. The next example is 27 plus 31. So I have the binary numbers 27 and 31 written down here. And we'll just go through the addition of these. So the addition of these first two examples should be fairly easy. You don't have to use 2's complement if you don't want to. You're just simply converting the decimal numbers to their binary and adding. So 1 and 1 in binary, of course, there's no 2. So 1 plus 1 is actually equal to what looks like a 10. So we write our 0 down here and we carry our 1 up at the top here. And so then we have 1 plus 1 plus 1, which in binary equals 11. So we write our 1, and then we'll go through and carry a 1. Then we have 1 plus 1, so we'll write our 0, and then again carry a 1. Then we have 1 plus 1 plus 1 again, which is 11 in binary, so we write our 1. We'll carry the other one. We have 1 plus 1 plus 1 again. So we write our 1, carry another 1. 1 plus 0 plus 0 is equal to 1. And so this looks like it fits into 6 bits, but we do need to recognize we have two positive numbers. So when you have two numbers with matching signs, that's always when you have an opportunity for overflow. So remember that if you have two numbers you're adding with the same number of bits and they have different signs, you don't have to worry about overflow, but if they have the same sign, you do. We could run out of room to write them. And that's just what happened here. So this number, it does represent the decimal number 58, but the most significant bit over here is a 1, and it does not represent that this is a positive number. So this is actually saying this would be a negative number here. And so what we would need is we would actually need 7 bits to properly represent this number with a 0 in front to show that this is positive. So what this means is that we have an overflow. We ran out of room in our 6 bits to properly represent this number and indicate the sign. Here we have our next two problems from question number 9. The first one is -4 plus 19. So I have built the 2's complement for -4. We'll hop over and take a look at that. Let's look over to the right of the screen. I have -4. So the first number I have is just how we would typically write a 4 in binary, right? We would have a 1 in the place value worth 4. And everything else would be zeros. So to convert 2's complement, of course, what we do is we invert everything, change the 1's to zeros, zeros to 1's, and then we'll go ahead and we'll add a 1. And so this is the number we end up with. So this is the number I have plugged in for -4, and then the number 19 is just simply the number 19 represented in binary. So if we go through and add here, we have 0 and 1 is 1, 0 and 1 is 1, 1 and 0 is 1 again, 1 and 0 is 1, 1 and 1, remember that's 10, or what looks like 10 in binary, so we write the 0 down here, we carry the 1, and then we have 1 and 0, which is 10, so we write the 0, we carry the 1 comes down. And so you can see we've run out of space. We've exceeded our 6 bits, but there's no overflow. And our first signal to that is that 1, these numbers, -4 and 19, are not of the same sign, so we can't overflow. They're opposite signs. And then the second is that if we take a look down here, this 1 is getting carried out. So this is a carry out, essentially. There's no overflow because the most significant bit, or the 6th bit, is a 0, and that's still representing that this is a positive number. So we can see that this is a positive 15. The rest of this number is representing 15. So this is just fine. There's no overflow here. All right, looking at our next example, 3 plus -32. So we'll need to find the 2's complement of -32. We'll go over to the right here. So I've written -32 as its typical binary value, and we'll go ahead and convert to 2's complement. So again, the first thing to do, of course, is just invert everything, flip it, and then we will add 1. And so it's actually, you see, it looks like the same number because 32 is the smallest number, the largest negative number that we can represent with this amount of bits and 2's complement. So it actually looks the same both ways. So we have -32 here. The typical way of writing the binary value of 3 is on top. And so adding these together, 1 and 0 is 1, 1 and 0 is 1, 0 and 0 is 0, again 0, 0, 0, again 0 and 0 is 0, and then last we just have a 1. And so we can see this number properly represents the number -29. We have no overflow, nothing extra, and our most significant bit down here is a 1, which represents that this is a negative number. So if we were to convert this back from 2's complement to a regular binary number and figure out what the decimal value of this would be, we would end up with -29. So there is no overflow here. Your fifth problem for question number 9 was -16 plus -9. So we can quickly recognize these are both negative numbers. We should not have an overflow here, but they're both negatives, so we'll need to do 2's complement for both. So if we look over here at -16, the first thing we do is write this out in typical binary form. So that's very easy. We just put a 1 in the place value worth 16. And then we invert everything, flip it all, and then we add a 1. So here's our value for 16 that we're going to be using. And then we have our -9 that we'll go ahead and convert. So we have 9 written in typical binary form. We are inverting everything, flip all those numbers, and then go ahead and add 1 to those. And so this is the numbers, or these are the numbers that we'll carry over here and use to add together. 0 and 1 is 1, 0 and 1 is 1, 0 and 1 is 1, 0, 0, or 0. 1 and 1, we write the 0 and we carry the 1. And so then we have 1, 1, and 1, which means we write the 1 and we carry a 1, which comes all the way down here. And so you can see we do have an extra bit. This would be a carry out, right? We have an extra, but there's no overflow because one, they're both the same sign, so there can't be an overflow, but as just a confirmation to get you in the habit of checking for this, we can see that this most significant bit, our sixth bit, that should be our most significant, is a 1, and it's still representing a negative number, which is correct. And so we can check this by taking this entire number that we have, discarding the one that we carried out. We don't need to worry about that. So we can take this whole number over here to the right. And just a reminder, whenever you end up with an answer that is a negative, we can flip it back and figure out the correct decimal answer. Or not the correct answer, it's still correct, but getting that decimal equivalent. And so I'm just carrying the number that we ended up with all the way to the right here, 100,111. And so to convert it back, remember, from 2's complement, we do the same thing. We just invert, so flip everything, and then we add 1. And so we have to remember this is negative, right? Our most significant bit was a 1, so that makes this a negative. But when we look at this in binary form, this is the number 25. And so we confirm this is correct. Negative 16 plus negative 9 should have equaled negative 25. So we're on our last part of question number 9 now, negative 27 plus negative 31. And I'm just realizing I may have misspoke on the last side. I think I may have said there can't be an overflow if the signs are the same. I should have said the opposite. An overflow can happen when you have the same signs. An overflow cannot happen if you're adding two numbers that have the same amount of bits with different signs. So overflows are tied to two numbers with the same signs. So remember that. And so let me add that correction there. So the first thing we need to do with these two negative numbers is to convert them to their 2's complement. So we'll start with negative 27. So I've written 27 just in regular binary form right here. We'll go ahead and flip. We're going to invert all the bits, and then we're going to add 1. So this is our negative 27 written up here. And then we have negative 31 written just as 31 in binary. And then to get the negative version, or 2's complement version, to represent the negative, we're going to invert, add 1, and that will come over here. So now let's add these together. We have 1 and 1 is 0, 0 and 0, 1 and 1 is 10 in binary. So we write our 0 and we carry our 1. Got a little bit ahead of myself there. And then so now we have 1, 0, and 0, so we write our 1. 1 and 0 is 1, 0 and 0 is 0, 0 and 0 is 0. 1 and 1 is 10 in binary, so we write the 0 and we carry the 1. And then of course that comes down and is just a 1. So now we have to figure out, is this a carry out or is this an overflow? Let's look at our most significant bit here, or what should be our most significant bit in the 6th spot, and it's a 0. So that's indicating that this is a positive number. We know that can't be true because we've added two negatives. So there's a potential for an overflow. So our result should be negative. Our most significant bit is indicating that this is a positive number, which is incorrect. So we've overflowed. We would need 7 bits to properly represent this number, but we're limited to 6. So it is an overflow. And this answer over here, contained within the first 6 bits, would be incorrect. So hopefully you found that review of homework 2 helpful. If you have any other questions, of course, feel free to email me, post on the Q&A discussion board. Now we'll go ahead and jump into our Exam 1 review. Your Exam 1 will be available next week. That's week 5. It's going to be worth 150 points, which will be part of 15% of your course grade. So this is a big chunk of your course grade. It'll be very important to be prepared for this exam. You'll have 15 multiple choice questions and you will have 11 open-ended questions. So 15 multiple choice, that means obviously you'll have multiple answers to select from, and the 11 open-ended questions will be things similar to what you've been seeing on your homework, to where you'll have to do conversions, calculations. You won't be picking from a set of answers, you'll just have to provide whatever answer you arrive at. Your exam will be closed book and closed notes, but you will be allowed a calculator. Now we'll look at the content in exam 1. I won't review examples of every single one of these. Typically, I would review examples in class, but because you have the recorded lectures, there's really no need for me to do that. You're perfectly capable of going back and rewatching those lectures. And then we've just reviewed some common mistakes that happened on homework 2 to clarify those, hopefully. So hopefully between those two things, the homework reviews and the original lectures, that's enough material for you. And again, of course, if you have any questions, feel free to reach out. So your exam 1, it's going to be important to be familiar with decimal, binary, and hexadecimal number systems. Know the base of those systems. Know what a bit is, what a byte is, and what a nibble is. You should know the definitions of those. Just a quick reminder, a bit is a single digit in a number, a byte is 8 bits, and a nibble is 4 bits. I will explain that one for you. And then you'll also need to know how to convert between these three number systems. So if we're going back and forth, how do we do that? You'll also need to know how do you add binary numbers together, how do you convert to get a 2's complement, how do we write signed binary numbers, and how would we add if we needed to use 2's complement numbers. For exam 1, you should also know the basic architecture of microcontrollers and microprocessors. So essentially everything that you see in this image here, we've covered, we've broken out and explained. So you should know the definitions for all of those, and you should know which of these pieces of architecture go in a microprocessor versus which of these would only be found in a microcontroller. You should also be familiar with the basics of each of the memory types that we've covered. So RAM, ROM, DRAM, dynamic random access memory, SRAM, static random access memory. You should know the definitions and kind of how each of these work. And to round off the memory types, PROM, EEPROM, and EEPROM. So essentially all the memory types that we've covered, and I don't think I added flash memory here on this slide, but you should also be familiar with flash memory. And I think most of you are, usually after writing a report on something, you're well enough acquainted with it, but that's not on the slide, but you should be familiar with that and know kind of some of the basics about it for your exam. You should also know about the different logic gates that we've covered, so and, or, not gates, and combinations of those different gates. You should know how each of these gates function and what do the truth tables look like for each of these gates. We also talked about some different languages, and so you should be able to recognize the difference between a high-level language and a low-level language. So please remember this kind of chain here that I've provided. We didn't cover the intricacies of like MATLAB, Perl, Python, Java, or C yet, but you should be able to recognize that Python is a more complex language than C, MATLAB is a more complex language than Python, and so on. So you essentially need to know the hierarchy of these languages and the difference between high and low. So again, high is a very complicated programming language. MATLAB would be a high level, and low level is a very basic language. So at the very bottom here, we have machine language. So be familiar with those and kind of the rankings of each of those languages. So now that we've reviewed your homework 2, we've reviewed what you should be studying for your exam 1 next week. Now we're going to get into the course content for this week and what we'll be doing in our lab. So this week's content will be focused on repeat actions when we're programming. Sometimes we need to perform the same task multiple times. So instead of rewriting that task again and again and again in your code, we can do that a little bit more efficiently with certain repeat actions or repeat commands. And it's important to recognize that when we're using assembly, the way that we do this is a little bit different from some of the more modern high-level programming languages. Essentially, modern languages are a little bit easier to do this in. We can use while loops. So while this is happening, do this. Or we can use if then else formats. So if this is happening, then if X is happening, then do Y, or else do Z. So we can kind of redirect our processor to different lines of code depending on what's going on. We can do this in assembly language too. It's just a little bit more difficult. In assembly language, we use jump instructions and conditional branching instructions. So we will take a closer look at those. And you might be thinking, if it's more difficult, why are we learning it first? We start with assembly, we kind of start at the ground floor, and then I think you'll see that when we get into C language, it'll be a lot easier to catch on. You should have an easier time with that. So we're kind of tackling the hard stuff first, and that should make everything else seem a lot easier. When it comes to using repeat commands in our code, we're going to be using labels a lot to help with these redirects, so that's the point we're going to start at. So we use labels to identify certain sections of the code for looping and branching. It's almost like a street sign, right? If you're using your GPS is going to tell you which street to turn on. Kind of similar to that, we can tell the code to go to a certain line based on the label that we assign it. So labels are always written on the far left. You'll notice in the example over here, typically when we write a code, we have our main instruction all the way to the left and everything is tabbed over underneath it. So labels also go all the way to the left and everything else should be tabbed over. This is for two reasons. One, it's how the processor will read your code, and two, this makes it a lot easier to see. So the labels, if they're all on the left, you can easily see where the processor will be jumping to and which sections of code are falling under each labels. It's also important that when you're choosing a label, it doesn't look anything like an existing assembly command. So essentially, a label can be anything. You could call a label here, we have it as sub1. Maybe this is representing subroutine 1. You could call a label loop 1. You could even call it label 1. You could name it something ridiculous like cookies, or you could give your labels different colors like blue, red, whatever you want to do. As long as your labels are not similar, they shouldn't look like any existing commands because that'll confuse the processor. It won't know if it's a label or if it's a command. So you wouldn't want to have the MOV be your label. That would be a poor choice. So make sure your labels don't match any existing assembly commands. Other than that, they can essentially be whatever you want within reason. Now we'll take a look at some different types of branching, and these are going to be using MIPS. So this is what's outlined in your textbook. What we use is a little bit different than that, pairing that with our little microcontroller, but it's important to be aware of different ways that we can program in assembly language. So we're still going to cover both. So we'll be covering this first. In this snippet of code, you can see that target is the word that they've chosen to use as their label. You can see the comments are a little bit different too. So instead of a semicolon, the number sign is used. So they're identifying that as a label. And so when we're using branching, we have two different kinds of labels. We have conditional labels that are based on a certain condition. If that condition is present, then that branch will be taken. And then we have unconditional branching, which means no matter what, you're going to go to this path. So the first type of branching we're going to look at is branch if equal. And of course, what that means is that if the two specified values are equal, then that branch is going to be taken. So we'll look at this line in the code here. So we can imagine our processor stepping through the code. It's performing some addition, it's performing some other comparisons. And so then we get to this line, BEQ. So that's the command for branch if equal. So what it's going to do is look in register S0, register S1, and if these two values are equal, then it's going to branch to the label target, which would take us down here. And so when we branch, what that means is that we are skipping these other lines of code. And we can see these notes on the left that they're not executed. We're skipping those in favor of the branch. And so we're saying that if the values in the registers S0 and S1 are equal, then what we're going to do is add the value of S1, the value in it, register S1 to itself. And so likewise, if the two values going back up here to the branch if equal, if these two values in register S0 and S1 are not equal, it's going to go through the rest of the code as normal. So it won't branch, it'll go down to the next line. And so branch if equal means it's only following the label if the comparison finds the two values to be equal. Similar to the branch if equal command, there's also a branch if not equal command, which is represented by BNE. And so this command, as you might imagine, it only takes the branch, it only goes to that label if the two values are not equal. So we had branch if equal, we could do a comparison. If they matched, we would go to the label or the branch. And so we also have a branch if not equal. So if these two values in register S0 and S1 are not equal, then in that case, we will take the branch. So you can use these different conditions depending on what you need to program for. If you're looking for two registers or memory locations or values, if you need them to be equal before you move forward, you might want to use a branch if equal. If you want these to be different to move forward, you can use a branch if not equal, and then that will take you forward to your target. So just a second ago, I mentioned that we have conditional and unconditional branches. Conditional branches are, of course, based on a condition, right? We were comparing if two values were equal, and if they were, or if they were not, we were jumping ahead to the label or to that subsection in the code. So we also have unconditional branching that where we branch no matter what. When we get to that line in the code, we're jumping ahead to our next subsection, our next label. And so when we're using MIPS, the jump command is just represented by a J. And so you can see we're performing some addition in these first couple lines of code. We get to this third line down, and unconditionally, it doesn't matter what any values are, we're going to jump down to the label target. So this is an unconditional label. No matter what happens, we'll be jumping down to this label or this part of the code. And so you can integrate these branches based on what you want the code to do. And later on, we'll look at a couple examples of why we would need to use branching, but essentially it builds decisions into your code. So you don't have to make the decisions for the code, it can run itself, and it adds kind of checks and balances into the code so we can carry it out, check values, and keep going and performing actions based on the state of things. Our last unconditional branch code was just jumping to a label. In MIPS, we can also jump to a register. So here in line 2, you see we represent that with JR as our mnemonic there. So J is just for jump to a label, JR is for jumping to a register. So here we're telling the code to jump to a specific register. All right, so again, all of the branching kind of codes that we've talked about before, you might have noticed they're written a little bit different. Again, that's because they're for use with MIPS architecture. Our architecture is a little bit different because of the specific microcontroller that we're using. So our coding is a little bit of a variation of those. And so one of the things that we can do with assembly in conjunction with the microcontroller that we have is looping. So this is essentially the same thing as repeating, right? Where we're going to certain sections of the code. We can use a loop rather than a branch to repeat the same section of the code a certain number of times. So instead of copying and pasting and saying increment register 7, increment, 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 we can just create a loop. You can see in this image down here that will increment register 7 5 times. And so the advantages of using loops are that this shortens the code, so it's a lot easier to debug. It's also much faster to write. and it reduces the chance of error, right? So if you have to write something 5 different times, that's 5 times the chance for error, whereas if you write it once, you have a better chance of getting it right the first time and not making a mistake. And so here we can use our loop command, and what that looks like in our program is just dot loop followed by the number of cycles. So here we see we want our loop to be carried out for 5 cycles. And so in my loop, you can have anything in your loop, but in my loop, I'm choosing to increment register 7. So I'm going to be adding 1 to whatever's in register 7. And then we're going to end loop. So a dot end loop is what ends this, and then it will go back to the other lines of code below that. So this loop, again, is incrementing the contents of register 7 by 1 each time, and it will go through this loop 5 times. So when we're setting up loops this way, we don't need to use labels. Our dot loop and end loop takes care of this, but this is one way to perform a loop a certain number of times. So the looping that we just looked at to use with a microcontroller is essentially an unconditional branch. It's going to loop no matter what. It's similar to just jumping back again and again and again to that point. We also have some other mnemonics that we can use with our MSP 430 that act as branches for us. So branches, meaning we can use these commands to help make decisions based on certain values. So here's a little table of commands that we can use. We can jump to the label if the 0 bit is set in this first one. We can jump to a certain label if the 0 bit is reset. And so what this refers to, you might have remembered that we have special registers when we're programming, right? We have the 0 register that flags if the sum or if the answer to some numbers are 0, if the result is 0, that 0 register flag is set with a 1, or it can be reset to a 0 the next time around. So based on if it's a 1 or a 0, we can use these two jump commands. We can use JC to jump to a label if a carry bit is set. So if you add 2 numbers or subtract 2 numbers and the carry bit is set, something is carried, we can jump if the carry bit is reset or if it is equal to 0. We can jump if a negative bit is set. We can look at that, or we can jump unconditionally, much like the J in MIPS. JMP is the mnemonic for this system, so that we can jump to any label unconditionally in our code. And so all of these jump commands have to be used with a label, right? We're jumping to a particular label, so you'll want to use labeling. And to go back to a different place in your code, you'll have to use another jump command and a label if you need to circle back. And so you might notice these first two, it's giving you kind of 2 different ways to write these jump 0 codes. And so the easiest way to write these will probably be the ones on the right side. You'll probably find that these work best for you, to write these as JZ and JNZ. So now we'll go ahead and look at a couple of examples of how we can use these different jump commands to help our programming and why we would need to use these jump commands. Here is our first jump example that we'll take a look at. In this first example, we're using the jump if not 0 command. So what this command does is it checks to see if the 0 bit is set. So if the 0 bit is not set, then it jumps to the label, jump if not 0. If the 0 bit is set, meaning a 0 in the previous command has flagged the bit, then it will not jump. It will simply go to this next line of code. So in the examples for this week, I'm going through programming this and stepping through each line of the code, and we'll take a look at what the registers do, how the 0 bit is populated. So that'll be a more in-depth explanation. You'll find that in this week's video examples. But here I'll just go through the code real quick and cover what we are trying to achieve with this short little code here. So of course in line 1 we are starting our code with the main command. We always start with the underscore main colon. And then in the next line, the next 2 lines really, we are simply clearing out the registers that we're going to be using. So we know that they're empty. So we're going to use registers 5 and 6 in this code. So we'll go ahead and we'll clear those out, make sure nothing is in there, just as a good practice. And in the next step, we are going to set the value of register 5 to be equal to 3. So I'll keep track of that. We'll use the bottom right screen here. So B5, and then we'll also set B6 up so we can kind of keep track in our minds of what those values will be. Okay, so B5 is going to be 3, and again you'll see this better in the video example, but we'll just go through this with what we have for now. So B3 is set to 3, and then in this next line here, notice this is our label, so that means we're going to jump back to this portion of the code potentially at some point. We are going to add 2 to the contents of B6. So this right here shows you why it is so important to clear the register, clear some of the registers out before you use them, because register 6 is going to act as it's going to accumulate a certain number. So if we started with the number 17 and we keep adding 2, our result is going to be very different, of course, than if we clear that register out and start with 0. So we know that we started with 0 because we cleared it. So now register 6 is equal to 2. Okay, now our next line is to decrement or subtract 1 from register B5, and so now B5 becomes 2. And then there's a jump if not 0 to label 1. So what this means is that if B5 is not equal to 0, we're going to jump back up to this label. If B5 does equal 0, we'll move forward with the next line of code. So the register B5 is essentially acting as a counter for us. We have the value of 3 in there, right? Or that's the initial value that we put in there. So what's going to happen is that the value of 2 is going to be added to register 6 3 times. We have that counter. Okay, so now this is just going to go back to our label 1, and we're going to add 2 again to B6. So that leaves us with 4. We decrement B5 down to 1. We do a jump if not 0 check. Well, B5 doesn't equal 0 yet, so we'll loop back to label 1. B6, we add 2 again. We get a total of 6, and then we are decrementing B5, so it becomes 0. Okay, so now that B5 is 0, when we get to line 7, the jump if not 0 command, well, now the 0 bit is set, so we're not jumping. What we're doing now is moving to the next line. And so all this line is doing is moving the value that we end up with in register 6, which happens to be 6. We're going to move that into a new register B7. And so if you changed the contents of register 5, essentially what is our counter, you could add more times to register B6, right? If you had 10 in there, it would add 2 to register B6 10 times, and we would end up with the value of 20. And then at the end, we're just moving that value into a secondary location or another register. And then that is, of course, END, the end of our program. So this is pretty straightforward. The JNZ, jump if not 0, is just checking to see if the 0 bit is set or triggered from the previous line of code. Here is our second jump example. I'm not going to go quite as in-depth on this one. I will leave that for the example video now that we've kind of seen how the jumping and the labels all work together, but we'll still step through each line of code. So in this example too, I'm still using a jump if not 0 command. And this looks a little bit similar to the last one. I've just added a couple things to try to keep some of the other variables consistent, right? So we're not introducing a brand new program. This is just the same program with a couple additional lines added. So I still have the jump if not 0 command. And to this example, I've also added the unconditional jump command. So remember, jump if not 0 is a conditional command. It relies on a condition to be triggered or activated or perform the action. And a jump command is unconditional. It happens no matter what. It doesn't matter what's in the registers. It doesn't matter what's in the status bits. This line is going to be executed. Okay, so let's go ahead and step through this code. Of course, we are starting with our underscore main. We clear out our registers in lines 2 and 3 as per the last code. Now you'll notice in this code we also have 2 labels. So label 2, so this action we're going to repeat at some point, most likely. We are going to move the value of 3 into register 5. And this is going to be our counter. If you ever don't want to listen through the whole explanation of these examples, you can always take a quick look at the comments where I just try to briefly explain what's going on. So if you're a little lost, of course you can rewind the lecture, or if you learn better by reading things yourself instead of being an auditory learner, learning by listening, it might be better to just pause the video and read the comments. That can also be helpful. Okay, so we've put our counter into register 5, and now again, similar to the last program, we're going to add the value 2 into B6. Now, same as last time, we're going to decrement the value in B5, so we're decrementing our counter, right? We're adding 2 to our cumulative total in 6, and we're decrementing our total in register 5. Same thing as last program, we are going to check if our counter is equal to 0, and if it's not, we'll jump back to label 1. So this part of the code is the same, where we repeatedly add 2, check if our counter is 0, if not, we add 2 again. Now, this is where it gets a little bit different. Well, in just a second here, I'm ahead of myself a little bit. So just like the last code, we're also still moving the result at the end into a secondary register, B7. Okay, now this is the part that's different in line 11. Here at the end, we are jumping to label 2. Now we're jumping up here. So we're jumping back to our counter, right? So what this program is doing is that when our counter counts down and gets to 0, we move the value into a separate register, the value of B6, right? We keep adding 2, keep adding 2, keep adding 2. Our counter's empty, we move it into another register. And here, this jump command creates a perpetual loop in the program. It essentially, when it moves up to line 4, or label 2, it resets the counter because it's moving the value of 3 back into our counter register B5. And so we repeat the process again. B6 increments, increments, increments. And then that value is added into B7. Why would we do this? Well, we are counting essentially up to 6, right, in this register. So maybe we want to increment one variable by 2, and we have another variable that we want to increment by 6, and we want to keep these synced up. So you'll notice we are not going all the way back to the beginning of the program where we cleared out these registers. And you'll see this more in the example video, but essentially B6 is not being cleared out. So B6 still has a value of 6 when we loop back up to label 2. And then we add 2, add 2, add 2. And the next time we get to the move command, it's going to move the value of 12 into register B7. So this is just a way to increment things in different values and keep them synced up. I would compare this to, think of a clock, right? When you hit 60 minutes, you, in a sense, are moving that value then to the hours, right? It looks a little bit different, but when you count all the way up to 60 minutes, then the hour changes. It's not quite the same because we don't keep counting up from 60. That part resets. But that's kind of the most similar and common analogy that I could give you on this. So this is how we can use 2 jump commands together, just in a very simple way. Lastly, we have our compare example. So a compare command can be used to test if 2 values in a register are equal. And so the compare command is usually used in conjunction with a jump if 0 or jump if not 0 command, because when the values are equal, it flags the 0 bit. That's the response. So if the 0 bit is flagged because the comparison is true, the numbers are equal, then what you need to do in the next line of code would be to check the 0 bit. And you can see in our example up here in line 7, we use the compare command to compare two registers, and that's followed closely, or right after, by the jump if not 0. So this jump if not 0 is essentially checking to see what the result was of the compare function. So we'll go through this line by line and see what's going on in this code as a whole. So of course on the first line we start with main to start off our program, and then in lines 2 and 3 we are just clearing registers 5 and 6. That's what we'll be using. In the next line, we are moving the value of 11 into register B5, and then we are moving the value of 15 into register B6. So we're populating both of these registers. Now I will add a note, if you plan on populating registers right away, you may not need these two clear lines. They're a little extraneous. But as you saw in our last example, we did need a register cleared out because it did impact the value. Or you might need to loop up to these at some point. So just a note that as a general rule, I think it's great to clear out registers. However, if you're writing hundreds and hundreds of lines of code, you may omit them because that time could add up. But I would recommend in your examples just clearing out your registers as good practice. Okay, so we've populated register 5 with 11 and populated register 6 with 15. Now we have label A, so presumably we'll loop back here at some point. This is the start of essentially our loop. We are going to increment B5 so that 11 becomes a 12, and we'll keep adding 1 to register 5. So we'll go 11, 12, 13, 14, 15, and so on. And so right after that, we are doing a comparison. We are checking if B5 equals B6. Well, 12 doesn't equal 15, and so the 0 flag bit is not set, right? So if the comparison is equal, then the 0 bit flag is set. If it is not that equal, then the 0 bit is not set. So then we have our next line of code, jump if not 0. Or what this is essentially saying is jump if these are not equal, right? If they're equal, the 0 bit is set. I know I keep repeating that, but that's what this command or these two commands hinge on, is that pretense of paying attention to the 0 bit and knowing what it means when it's set and what it means when it's not. So jump if not 0 would mean that these two did not equal each other. And so we would jump back up to label A. And this just increments B5 again. So we're essentially saying B5 is 11. Okay, increment, now it's 12. Is it equal to B6 yet? No. Okay, increment it again. Now it's 13. Is it equal to B6 yet? No, and so on and so on. And so once B5 is equal to B6, the 0 flag bit will be set. Again, look in the comments if you need a reminder. And that means this jump if not 0 won't be activated. We won't jump up to the label then because it is 0. The 0 bit is set. So we'll just move on to the next code. And here we're just simply placing the value of 4 into register 8. So that's just the result of this. There could be anything as a result of this comparison, whatever would make sense when you're programming. Of course, there will be specific scenarios, but in this one, once they're equal, I've just chosen to move the value of 4 into register B. And then, of course, we end the program by just typing end.